Hello, this is Jack Jackson. In this video, we're going to go over some solutions to some review problems from my first unit of Survey of Calculus. And these particular problems in this particular video are over the basic interpretation of derivatives and some limits. So some things at the beginning of calculus. So first question, explain informally what is meant by the limit as x approaches 5 of f of x equals 7. And by the way, that's how you would read that. Well, this means that as x gets closer and closer to 5, y, or f of x, gets closer and closer to 7. So another way to phrase that is if we make the output, we can make the output f of x as close to 7 as we want by taking x sufficiently close to 5. Is it possible for this statement to be true and yet f of 5 equals 12? Now what you should be doing when you're watching this video is pause each time I present a question, see if you can answer it yourself, and then check your solutions against my answers that I go through here. And the answer is yes. It is possible that there's a hole in the graph at 5, 7, so that the limit as x approaches 5 of f of x equals 7, but there's an isolated point on the graph at 5, 12. For an example, see this graph here. So here we have a line with a hole in it at 5, 7, right here, and yet there's an isolated point up here at 5, 12. This point up here, or whether or not there's a point here, or right here in the hole, or which case it wouldn't be a hole, or whether there's no point at all on that vertical line has absolutely nothing to do with the value of the limit. The limit's what's happening as x gets closer and closer to 5, but not equal to 5. Next, use a table to find this following limit. The limit as x goes to 1 of x to the 21st minus 1 over x to the 15th minus 1. Okay. Well, we can use a graphing calculator to look at some tables. So to do that, we're going to first put this formula in, say in Y1, here's on a TI-84. And so on a TI-84, you want to be sure you put the numerator in parentheses, and then divides, and then the denominator in parentheses there. And when we're approaching from the left side, we're looking at x values less than 1, but getting closer and closer. There's no hard and fast rule about exactly what you put here in the table, but they should be numbers less than x, less than the 1, and then they're getting closer and closer. And you see I've picked some, and I'm getting very close to 1 here at the end, and we see that the y is getting very close to 1.4. It's actually still always a little below 1.4 when we come from the left side, but it's getting closer and closer to 1.4, it looks like. And then we can also take the limit from the right side. We take numbers that are larger than 1, but close to 1, and getting closer and closer and closer still. And this last one, I let x be 1.00002, and we see again that y is very close to 1.4. So it looks like probably we're getting close to 1.4 for our limit, which is 7/5. Now notice this function is a typical one that we encounter in calculus a lot, where if we actually plug in the x equals 1, 1 to the 21st is 1 minus 1 is 0. 1 to the 15th is 1 minus 1 is 0. So it is of the indeterminate form 0 over 0. When that happens, the limit could be anything. It may not exist. It may go off to infinity or negative infinity. Or it may be some real number. It could be anything. That indeterminate form, 0 over 0, really doesn't tell us anything. It tells us we have to look more into it. When we look at the graph, it looks like that's going to be our limit. Okay? Now, if you try to graph this on a TI-84, for example, you may or may not see the hole, depending on how you have your windows set. There might be a little gap, which there appears to be one right here at the hole, but it may just try to connect up the points across the hole, and you may not actually see it. Okay, if you put this formula in Graphmatica, it will show the hole, and some other graphing programs will. Next, how about another limit? Find this limit if it exists. The limit is n goes to infinity of the square root of 16n to the 8th minus 3n all over n to the 4th plus 6. Well, the idea here is we can look at this a couple of ways. I'm going to use the graphing calculator here and formally do this, so we can plug in the formula here. Notice the use of the proper use of parentheses here, putting this in. And when we graph it, it looks like that as we're going out to the far right, which is what we're doing here, it looks like it does level off to an asymptote or level off to some value. And so that value that it's leveling off to or approaching is our, that y value is our limit. Notice, by the way, when I put it in the calculator, I used x's instead of n's. So in a table, then, we let x get larger and larger and larger, and we see that y is getting extremely close to 4, so it appears that the limit is floor. Now, there are some algebraic techniques we can use on this as well. If all you need is the limit, I think we probably already have it now. We could just stop there. But if we wanted to actually prove this was the limit, we would maybe use some algebraic techniques. And here's a technique that might work on this one, or that does work on this one. We can multiply the top and bottom of a fraction by the same number as long as that's not 0. So when you plug in any real number here, no matter how big, 1 over n to the 4th is not 0. Maybe real close to 0, but it's not 0. And you multiply the top and bottom of the fraction by that. So multiplying the numerator and denominator of a fraction by the same non-zero number gives you an equivalent fraction. So that limit will still be the same. Now, the n to the 4th is the square root of n to the 8th. As a fraction power, that would be 8 halves, which is 4. Now, let's see, we can distribute now, and let's do the denominator first. 1 over n to the 4th times n to the 4th cancels out, leaving you just 1, plus, and then 6 times 1 over n to the 4th is 6 over n to the 4th. Now, 1 over the square root of n to the 8th, when I distribute, is going to be this square root divided by that square root, which is the square root of this polynomial divided by n to the 8th. So let's just distribute that. 1/16 n to the 8th divided by n to the 8th is just 16. And negative 3n divided by n to the 8th is negative 3 over n to the 7th. Now we can use our properties of limits that says we can take the limit of each part here and put it back together provided all those limits exist. Of course, 16 doesn't change as n changes, so that's still 16. Same for the 1 here. But both of these fractions here, as n gets bigger and bigger and bigger, a fraction is going to get smaller and smaller and smaller when the denominator gets bigger and bigger and bigger, provided the numerator stays fixed. And that's what's happening here. So both of these fractions here approach 0, and so this goes to the square root of 16 over 1. Square root of 16 is 4, divided by 1 is 4. So there's a formal proof using some properties of limits. But again, if all you need is just the number, you can also do it from a table there as well. So you can go either way that you want on that one, for example. Next, let's continue informally to find a limit using a table for this particular function. And the limit is x goes to 5. Notice, by the way, if we plug in 5, we get 0 in the denominator, and so this is undefined. In fact, we get 0 in the numerator as well. But we can use a table as follows. Put the formula in for y1. This is the limit from the left side. As we put in things less than 5, 4.9, 4.99, getting closer and closer, I ended with 4.9999. And it looks like the y's are getting very close to 0.6. They're a little bit under 0.6 at this point, but very close. So it looks like that limit is 0.6 because they're getting closer and closer to that. On the right side, we can take the limit from 5 as x approaches 5 from the right by putting in numbers like 5.1, 5.01, 5.001, 5.0001. And again, we see the y's are getting closer to 0.6. So since those are the same, then that must be the overall limit. There I've written it out a little bit bigger in a table there. And so it appears that that limit is 0.6 or 3/5. Next question is confirm this algebraically. So we can do some algebraic techniques to this. So a little algebra that we can do here is factoring. This is the difference of two squares in the denominator, so that factors is, that's x squared minus 5 squared. So it factors as x plus 5 times x minus 5. The top factors as sort of anti-FOIL factoring, or the distributive property there basically backwards for FOIL. And to get the f to work out, you have to have x times x to get x squared, so that's x and x. And 5, negative 5, the only choices are 1 and negative 5 or negative 1 and positive 5. And the one that gets the inner product to work out is negative 4. Negative 5x plus 1x is negative 4x. Now, that is the fraction. Now, notice these x minus 5s are equal. And since x is not 5, these are not 0, so we can cancel. And we get the same limit. Now, this is a continuous function of what's left. And so I can plug in 5 here for x here and here. And we get 6 over 10. We're basically using some limit properties there on that step there. So algebra step here, limit property right here, and then arithmetic on out to get 3/5 or 0.6. What's the value of the function when x is 5? Well, it's indeterminate of the form 0 over 0. If you plug in 5 in the bottom, let's see, you get 5 squared minus 25 is 25 minus 25 is 0. Put in 5 here, you get 25. Here's negative 20 minus 5 is negative 25 plus 5. 25 is 0, and you get 0 on the top. Or if you plug it in here, you can clearly see that x minus 5 is going to give you 0 over 0 when you plug in x equals 5. So the fact that the function is undefined but it has a limit says there's a hole in the graph, also known as a removable discontinuity at the point 5, 3/5 or 5, 0.6. And so if we graph the function, there we see it graphed, you see a hole in the graph right there when x equals 5 and y is 0.6. All right, how about another rational function problem? Let f of x equals 5x minus 20 divided by x squared minus 2x minus 8. What's the domain? Well, to find the domain of a rational function, what you want to do is you want to factor. I'd rather mainly factor the denominator, but you want to factor the numerator and denominator actually. So I'm going to factor a 5 out of the numerator using a common factor distributed property factoring. So factor out of 5. That leaves x minus 4. Notice if you distribute this back out, you're back there. And then we do sort of anti-FOIL factoring here. To get x squared, you're going to have x and x. To get negative 8, your only choices are 1 and 8, 2 and 4, 1 negative, 1 positive. And the one that works out is 2 and negative 4. So this is 2x minus 4x is negative 2x. So once you list all the possibilities for this last one, it's a little bit of trial and error or guess and check kind of a thing. So this is the reduced version. Now don't cancel yet. We see that if x is negative 2 or x is positive 4, the denominator is 0. So the domain is all real numbers except for negative 2 and 4. And this is the most compact way to write it right here. Now this does reduce to this 5 over x plus 2, but only when x is not equal to 4. So we need to put that restriction. If you plug this in your table calculator here and plug the original in your calculator, they will agree to all points except at x equals 4. Well, this will give you 5 over 6, or a decimal version of that, and this will be undefined. Of course, at x equals negative 2, they're both undefined. So what are the discontinuities? Rational functions are continuous anywhere they're defined. So the only discontinuities will be these places where it's undefined at negative 2 and 4. And on rational functions, the discontinuities have to either be a hole in the graph or a vertical asymptote. And I can tell you right now that the x equals 4 is going to be a hole in the graph, and the y value that goes with that 4 is 5, 6. So 4, 5, 6 is a hole in the graph, and the x equals negative 2 is a vertical asymptote. So if it makes the 0, it still makes the denominator 0 after you've reduced that x value, negative 2 in this case, is a vertical asymptote. Whereas if that x value plugs in the reduced version and you get a y out, that y along with that x is the coordinates of the hole in the graph. So these x's here, negative 2 and 4, are the discontinuities. Now let's investigate limits as we go in there. Okay, and I've kind of already said this one, but the limit as x goes to 4 of f of x. Well, there's the function, and again, it reduces to this, provided x is not 4, but x is not 4, it's only approaching 4 for the limit. And so here we can just now plug in 4, and we see 5, 6, or in decimal form 0.83 with the 3 repeated. So again, that's a hole in the graph. And notice, again, you can see that reduced version here and the original version in the calculator. Notice you'll see an error message both places where you have the vertical asymptote, but we'll see an error message in the original and a number, the y-coordinate of the hole, when you have a hole in the graph. Also, all the other numbers are the same, so that tells you that we did the reducing correctly, the factoring and canceling correctly. Okay, now this should say. Now the next thing is to notice is notice in the, well, whether you're looking at the original or the reduced version here. Let's say right here. Notice if x equals -2, the denominator is 0, and the whole thing's undefined. But if x is a little bit bigger than -2, like -1.9, the denominator is positive. So we're talking about positive numbers when x is to the right of 2. That's going to tell you it's going to go to positive infinity from the right side of -2. But if you're a little bit to the left of -2 for x, like -2.1, this denominator is negative, and this whole thing is negative, so there's a negative. It goes to negative infinity. So what we should see then is the limit as x goes to -2 from the right side is positive infinity, and from the left side is negative infinity, and that's corroborated by the table here. As we put in x is closer and closer to -2, we get bigger and bigger values. Now this is not actually equal to -2 here. This is probably -1.999999 or something, and it gives you something really big. If you actually plug in -2, the whole thing's undefined. And again, this is not actually -2 right here. It's -2 point, probably 3 or 4 zeros and a 1, and to get that. Okay, analyze the end behavior. What happens as x goes to infinity or negative infinity? And on a rational function, it will be the same on, well, if it has an asymptote, it will have the same limit on both sides, okay, if a limit exists. So here we see that the power is bigger in the bottom. Anytime the power is bigger in the denominator, this limit will actually be 0. And you can corroborate that with the table here. You can see that these are getting close to 0. Now, by the way, this 5e -7 is 5 times 10 to the -7. So it's 0.6 zeros into 5. It's getting very close to 0. And also, as you go way to the negatives, get bigger and bigger absolute value, but negative numbers, you're also getting closer and closer to 0 for the y values. So we can look at it as a table. You may actually just know some theorems or things about rational functions there. Or another way to see this is if you multiply top and bottom of this fraction by 1 over x, you'll see that the top is going to go to 5, and then take the limit of each piece. You'll see the top's going to 5, and the denominator is still going to infinity. And that makes the whole thing go to 0. The fraction's getting smaller and smaller. We can also graph it. There's a graphing calculator graph. Now this one, notice we really didn't see the hole very well, but there was a hole in this one at x equals 4. I'm not sure the scale, but I think this is 1 each. So right about here should be a hole in the graph. And then we see the vertical asymptote here at x equals 2, -2. And you can see it a little bit better on this Graphmatica graph. You can see a vertical asymptote right here of this grid line right here at -2, x equals -2, and at 4 comma, was it 5, 6, I think, was the hole right there. All right, another rational function, identify the vertical and horizontal asymptotes. Well, again, we want to factor it out. The numerator doesn't factor over the real numbers. X squared plus 2 is always positive. The denominator, to get 3x squared, I'm going to factor out and make 3x times x. And for the 4, we only have a couple choices, either 1 and 4 or 2 and 2, either both positive or both negative. Since the middle is positive, they'll both be positive. The one that works is 2, so this is 2x plus 6x is 8x, so FOIL works there. So our anti-FOIL factoring. Nothing cancels here. Another way to write this is if I could factor a 3 out of this and make this 3 times x plus 2/3. So whether you're seeing it this way or this way, I think you can see that x equals -2 is going to make the denominator 0, and x equals -2/3 is going to make the denominator 0. And those, since they still make it in, this is the reduced version, they will be vertical asymptotes. No holes in the graph on this one. Let's look at this a little bit more. Specifically, which direction are the arrows pointing, you might say, or which way is it approaching that? Is it pointing going up or down? Are the one-sided limits infinity or negative infinity? We know it'll be one or the other because we know it's a vertical asymptote here. Now let's look first of all at -2. If x is near -2, when you add 2/3, this fraction is still it's negative anyway, right? It's near -2 plus 2/3, right, which is a negative number. The top is always positive. 3 is of course positive. So this would be negative. And now what about this? What if you're a little bit to the right of -2, like -1.9? Then this would be positive. So you'd have positive, 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 negative here. That all multiplies together and divides out to be negative. And as the bottom of this fraction goes to 0, the whole fraction is going to go to infinity, or negative infinity. In this case, to the right of 2, we said this is positive, this is negative, should go to negative infinity. So -2 from the right side right here, negative infinity. We'll see this in the graph as well. If you look at negative, as you go to -2 from the left side, that factor is still negative. These are still positive. But this one would be negative, like -2.1 here. This would be negative. And the whole thing is positive, so that's going to go to positive infinity. And we could look at -2/3. When you're near -2/3 and you add 2, that's positive. So everything's positive except for this fraction, this factor right here maybe. So if -2/3 x is equal to -2/3, of course, that's 0. But if x is a little bit bigger than -2/3, when you add 2/3, you're going to get a positive number. So the whole thing's is positive. So the limit as x goes to -2/3 on the right is positive infinity. Whereas if you put in a number a little bit less than -2/3, that limit from the left, will make that factor negative. All the rest is positive, so it goes to negative infinity. Of course, we can see this in a table here as well, or a graph. Here's a graph, and we see those vertical asymptotes here, -2/3 and at -2 here. And we see that if we plug in -2 or -2/3, which is right here, we get error messages. But if we plug in stuff that's close to it, we see these asymptotes, asymptotic behavior here. For example, -0.666 is a little bit to the right of -2/3, and we get a really big number. So that's going way up here. So that indicates maybe a positive infinity there. And -0.667 is a little bit to the left of -2/3, and notice down there it goes way down in the negatives. So that's the limit going down to negative infinity. -1.999 is just to the right of -2, and notice the y value is way down. So that's this one right here, going to negative infinity, and going a little bit to the left of -2/3, like a -2, like -2.001, gives us a really big number. So that's going up to infinity here. Now what about limits as we go to infinity? So whether you're going to positive or negative infinity, it works out the same way. What you can do algebraically is multiply top and bottom by 1 over x squared and distribute. And notice that this x squared times 1 over x squared is 1. This gives us 2 over x squared. 1 over x squared times 3x squared is just 3. 8x times 1 over x squared is 8 over x. And 4 times 1 over x squared is 4 over x squared. Now we can take the limit of each of these little pieces, and each of these fractions here with a constant numerator and an x for the denominator, or x to some power for the denominator, whether you go into infinity or negative infinity, all those go to 0. Of course, 1 and 3 are just fixed, and so the whole thing goes to 1/3. And you can do a similar technique like this at all times that you have a rational function like this, where the powers are the same in the top and bottom. The biggest power, the degree, is the same in the top and bottom. And what happens is you always get just this ratio of the coefficients, 1, whatever this coefficient is here, 1, over whatever this one is, 3. So it goes to 1/3 in this case. And if you know that theorem, you could probably just do this in your head then. It's just 1 over 3. And of course we could check that with the calculator by plugging in something really big. Here I put in 100,000 for x, and notice it's very close to 1/3. 1/3 of course is 0.3 repeating, and I'm close to it already there. If I plug in something negative but really big absolute value way out to the left, it's going to approach the same thing. So here I've put this in. This I used the new version of the calculator operating system on a TI-84 and did the inner fraction thing and typed in the numerator and denominator like that. But if you use the older version or just use the other technique, you'll be with the slanted fraction line, you'll need to be sure to put parentheses around the numerator and denominator. That blacked out square is negative, so this is going from -10 to 10 on both x and y, and that's the graph that we saw. And sure enough, we see some kind of horizontal asymptote. It looks like it's a little bit above 0. It's actually at 1/3. So some of this stuff I've kind of done it more than one way. We can look at it. The easiest way I think to do is to look at the graph at the factoring, and you can tell the vertical and horizontal asymptotes just by looking at that. Once I got the x equals -2/3 and x equals -2, boom, we're done with that. If I just want the vertical horizontal asymptote, then since the powers are the same here, it's just a ratio of the leading coefficients, so it's y equals 1/3, and we're done there. So if that's all you have to do, you could just get it done that quickly. But you also saw me analyze that a little bit more with calculus here with the limits. We could also see that with the table and the graph, and that can help us reinforce those answers. All right, now we have a function here, and I've asked you to find a whole bunch of different limits and function values. And the interesting places where we might have limits and function values are the places where there are discontinuities. So basically what I'd like you to do, if you're working along with me here, is just pause the video here in just a minute and find all the x values where we have discontinuities, and then compute all the limits, left and right limits and full limits if they exist at all those places, and evaluate the function at all those places if they exist. Press pause now. Okay, well, let's look at this. Here we see we have discontinuities, breaks in the graph when x is -4, when x is 0, x is 4, x is 8, and x is 10, and x is 12. So those are the interesting places. So let's just kind of talk about all those limits very quickly. Notice that f of -4 is +1 because there's a dot on the graph right there. The limit as x goes to -4 from the left side is coming this way. It's approaching +4. The limit as x goes to -4 from the right side is following this graph, and it goes to infinity, positive infinity, which means it doesn't exist. F of 0 is 4 because there's a dot right there, an isolated point. The limit as x approaches 0 from the right is 0, and the limit as x approaches 0 from the left goes to infinity. So it's undefined. So the full limit as x goes to -4 does not exist, and neither does the full limit at 0. Now let's just take a place where it's continuous for contrast. Let's say 2. F of 2 is 4, and the limit as x approaches 2 is also 4. And so that is a nice connected point there, continuous point. On contrast, f of 4 is 16, and the limit as x approaches 4 from the right is also 16. So we might say it's right continuous there, but it's not a continuous function. We have a jump discontinuity because the limit as x approaches 4 from the left is 8. Okay, so we have an open dot boundary point there at the origin and at 4, 8, and also at -4, 4. We have isolated points at -4, 1 and at 0, 4. We have a closed dot boundary point up here at 4, 16. Now, we have a hole in the graph at 8, 8. So the full limit, whether you're coming from the left or right, or the full limit as x approaches 8 is also 8. So 8, 8 is a hole in the graph. We have a left continuous thing here where we have a point on the graphs at 10, 4. So f of 10 equals 4. And also the limit from the left as x approaches 10 from the left of f of x is also 4. And the limit as x approaches 10 from the right is infinity. Doesn't exist. At 12, we have another hole in the graph, and f of 12 does not exist. F of 8 did not exist either. F of 12 is, well, it's 4 point something. I'm going to say it's about 4.6. And that's the full limit as we go in there. So f of 12 doesn't exist, but the limit approaches, say, 4.6 there. So here are some of the answers to the questions that I ask over here is some of the limits. And we just went over all of these. Pause that if you want to look at the notation and write those down. So we've got some more problems in this review set, but I'm going to come back to them actually, and I'm going to actually put them in another playlist. This is going to be in my first playlist for calculus, talking about limits. The second one is the next part is going to be talking about derivatives. It'll go into the derivative concepts playlist, the second playlist, and the third part is about derivative formulas and using those, so that'll go into the third playlist. But all of these are in the first unit for Survey of Calculus. Overall, these 3 videos will give the students a pretty good review for the exam and the practice test.